Hey, how's everyone doing today? Good to see you. Meet Sierra, KP. I saw KP. It says Mebot's. Oh, Mebot's like catching up. In assignment, what does churn mean? Churn means if we lose a customer. Good question right there. Good to see you here, Kevin and Isabel. Let's go take a look at the project. People are wondering. Sorry about the late start right here. It's Friday. We're gonna get some work done on Friday. That's what we say. Friday time for work. Let's see. Joining into Canvas. I did change my NetID password, and it's like making me log in like 20 times these days. It's like relog in. I'm like, okay, I've logged in. I've logged in a lot. And let's go over here to the project. And for the project, do we need to just show jump t-test on a one sample t? The directions don't have it for the summer class, but had in your video for the spring. Go by the directions on the project. So let's take a look at that, Cooper. You're talking about do we need to show a jump? Yeah, you would show the test. So we could talk about the one sample t here, Cooper. I could go over how to do that. We could talk one sample t to start. So let's talk about the project a little bit to start, and then we'll probably do the one sample t. We'll make sure. So let's go here, stat 201. Project 2, let's over to the main screen. Let's do it. Okay, so here is the project. Now, if you're wondering, we've got the documentation right here. It should go into detail on churn, right? Yeah, oh, so he says, so churn is an industry term, which means you lose the customer. It means like they did not renew their contract. Churning is a bad thing. So we want to figure out why customers are doing that. So it's an industry term. So I guess I've heard it too many times. And you're like, churn? What is churn? Like, I wonder if I go, my computer's being all crazy. How do we do time series cross-validation for AIC? I tried to do it and check returns RMSC, things like that. Let's do that here in a moment, Sierra. You got it. We need to talk about that today in class. Some AKEK's information criteria. Good question, Sierra, right there. Churn in cell phone. Oh, churn in business. It has it right there. 2 seconds. For 2 sample T, do we have to use the same Q and categorical? You don't have to. You could if you want, as long as it's a quantitative and categorical variable. Churn rate. Here it is right here. Churn rate definition. The churn rate, also known as rate of attrition or customer churn, is the rate at which customers stop doing business with an entity. They leave us. They churn. I guess I've heard that term too many times, but churning is a bad thing. You crack the code right there. So it's most commonly used, expressed as a percentage of service subscribers who discontinue their subscriptions within a given period of time. It's also the rate at which employees leave their jobs. So it's used there too, but I hear it for like customers. Does that make sense? So industry term, basically the churn rate measures a company's loss in subscribers for a given period. So they churn. I don't know. I've just heard it so many times. It becomes one of those words like, oh no, we lost customers, but it's the churn rate. So you don't want a high churn rate. But looking at, do we want to do the one sample T and then some 475? Also, we're going to talk about project in class 474. We'll talk a little, yeah, KB, you got it. It is up there. It is basically just doing what we've been doing, but just with a data set. We've got the last assignments posted for 474, 475. We got the project for 474, 475. What are we going to do right now? Take a vote. Let's see here. 474 project, 201 one sample T, or 475. I'm gonna make this a quick vote. So if you're listening now, take a vote right now. Which of these are we gonna do? If you're here, you get to vote. 474 project. We're gonna end the poll in 10 seconds. I'm ahead of you in the future, so you'll see it end. Oh, it might be a tie. Let's find out. Okay, time to end the poll. Were there only 2 votes? Let's see. It was 50. Oh, it's 10 votes? Whoa. Wow. Okay, so there's the order. So we're gonna make sure to get to AIC. Let's run this in this order. You ready? Okay, so we got project for stat 201. There are more, so they might have went out. Project one sample T. Then we got BS 474. Final project. Then got BS 475, AIC in TM series cross validation. Okay, let's talk about the one sample T for the project. So when we do a one sample T, what are we doing? when we do a one sample t, what are we doing? Who knows when we would use a one sample t? Does anyone have any idea when we would use a one sample t? This is an important question which goes to your tools and techniques. So you have to know when we would use a one sample t. My Stream Deck is acting odd because I clicked the button and it's not going away. When would we use a one sample t? Who knows when we would use a one sample t? It says on. There we go. Cloud it off. There we go. Something when with the true mean. Great job right there, Kevin. That is true and quantitative. So when we're testing one quantitative variable. Now a two sample t compares two means. A one sample t looks at one mean and compares it to a value. So can anyone tell me a variable on here that we could do a one sample t test with? What variable on here could we do a one sample t test with? Any variable, just name it. Be like, okay, I could do a one sample t test on this. So now you're not going to use two variables, you're just going to use one. So a two sample t test compares the mean of two groups. We talked about that yesterday. A one sample t test just looks at one quantitative variable. It doesn't compare it to two different groups. It just looks at one quantitative variable. So what would be a possible variable? Take your pick. GPA, yeah, let's go ahead and do GPA right there. Now, all we're going to look at is GPA. Great job, Knox, KP, and Meets right there. So we could look at GPA or age. We could look at age. So when we do this, we'll go to Analyze Distribution. This is not a fit y by x because fit y by x is bivariate. That would be comparing a y variable of interest to over an x variable. So two variables would be used in fit y by x. We're just looking at one distribution of one variable. Let's go ahead and put our quantitative variable right here. And this is the one quantitative variable for the one sample t-test that we're analyzing. So let's take a look. Now you see the histogram. Now, here's the thing. This is pretty normal-ish. There are some outliers. We'll zoom in on it right here. There's some outliers. It's really unimodal, somewhat symmetric, some extreme outliers on the far side down here. But overall, pretty normal. And because the sample size is so large, we could probably go ahead and let's look at that sample size. The sample size here is 806. We could probably go ahead and use the one sample t methods. What are the three conditions for doing the one sample t? Hint, the first two are pretty much gimmies. So what are the three conditions for doing a one? The easy ones. We'll give everyone here a second to think about it. But the three conditions for the one sample t, this is your time to practice and see if you know them. To do the one sample t, we'll add a little histogram count axis right there. Go to hey, what's up, Noah? Good to see you here. I'm gonna take a look at the app a little bit. Random. Did we randomly take the observations? Great job, Mikhail, right there. It's less than 10%. Did we sample less than 10% of the population? If this is UT students, we probably sampled less than 10%. Now we have to pause. When you get to the third condition, you have to pause. You put those pause in the chat. And what's the third condition for the mean? When we do the mean, what is the third condition for confidence intervals or testing the mean? What is the third condition? This is where you have to pause. You have to slow your mind down. You have to say, okay, third condition is based on, are we doing a quantitative or categorical variable or the chi-squared? So what is the third condition when we are testing the mean? What would the third condition be? What is the third condition? Who knows? This is the tough one that people get wrong because you can do random, 10%, and then you have to say, okay, wait, am I dealing with categorical? Am I dealing with quantitative, or is it chi-squared? This is where I want to see what people answer. Don't worry if you get it wrong. Nearly normal, Meath, you got it. You're right. It is nearly normal. So success failure is for categorical. So, and don't worry, right there, Rajvi, 100 points for taking a good guess at it. So had we done something like born in Tennessee is categorical, and the third condition for born in Tennessee to make a confidence interval for that, which we're not doing right now, I'm just showing, if we had done confidence intervals for born in Tennessee, this top one would be success failure because it's categorical. Are there at least 10 successes, at least 10 failures? And then this bottom one is quantitative because high school GPA is a quantitative variable. So its third condition is nearly normal. Does that make sense to differentiate the third condition right here? The top one is categorical. So, because are you born in Tennessee? Yes, no is a category. And the third condition is thus success, failure. Are there at least 10 successes, at least 10 failures? And then the bottom right here is quantitative. How much is your GPA? Weird way to ask it, but it's a quantity of GPA, which you can compare numerically. And thus, we would have the third condition be nearly normal. You can also kind of see, you can look at the shape of this one, where bar charts really don't have a shape because the bars could be in any order. So good work right there. The third condition would be nearly normal. Now, when we do the test on the mean, talking about some ROC right there. When we do the test on the mean, the test looks the following way mathematically. For 474, when's the, I think we'll do it on Sunday too. A lot of review on Sunday. Sunday. Reviewing all Sunday. S over square root of n. What is this? What does that value mean right there? What is that value? So we have here the sample mean. We have here the sample standard deviation, the sample size. Kind of, you're close. It's, there we go. It's the true mean. The true, oh wait, it's kind of the true mean. Mu is the true mean. Mu is the true mean, but it's mu naught. It's mu naught. So mu is the true mean, but it's mu naught. So it is mu, it is true mean, but it's mu naught. So you're very, very close. Got some pointers in the chat. So it's mu naught. So in the output, we see right here the sample mean, the sample standard deviation, the sample size. But what is mu naught? What does the naught mean on it? Let me give you a hint. P naught is the hypothesized true proportion. P naught, like when we do the equation, if I did the equation, which we're not doing right now, but we could show it, P hat sample proportion minus P naught true proportion over P naught hypothesized true proportion times Q naught hypothesized true proportion over N sample size. So the naught means it's what? Hypothesized true mean. Exactly. We're just hypothesizing an amount. So what amounts can you hypothesize are true? Anything you want. These are all hypothesized. Hence why when we write the hypothesis test, we do the following. In a hypothesis test, we write something like the null hypothesis states that the true mean is equal to some hypothesized mean. Or over here, we would write the null hypothesis states that the true proportion is equal to some hypothesized true proportion. Now, usually we go in and we hypothesize a value like 3.8. So 3.8 would be mu naught. Does that make sense right there, Meet? So mu naught is like the hypothesized true proportion. Good to see you here, Aisha. It's going to be what we hypothesize is true. We're just saying, I believe this is true. You can take a guess and say anything is true. So when we do this test right here, all we do is go over here and go to t-test, and we tell it the value we are hypothesizing. So this is mu naught right here, and we don't do a z-test on this, we just do the t-test. And so with this right here, this is your mu naught, just reviewing it again in notation, that value right there is mu naught, which would get plugged in, and I can kind of guess this for you, or I can run the test pretty quickly. Oh, the t-statistic's going to be tiny, so the t-statistic should be I made a typo. .022. Whew. And the p-value is going to be close to 100%. What am I doing? I'm making typos today. 3.8. Oh, I used the standard deviation. I used the standard deviation. I thought I was using the standard error. I meant to do, when Brian goes too quickly, I thought I grabbed the standard error, but I looked at the wrong one. We should divide by the standard error, which is s over square root of n. I grabbed the wrong one. There we go right there. There is the t statistic right there. And that is s over square root of n is the standard error of the mean. So this is the t-test. This is the hypothesized value, which is any value we can use. Jump is going to go ahead and do all the work for us that we would have to do by hand, so we don't have to worry about dividing the mean by the standard error or the difference from the hypothesized mean by the standard error, which we would do by hand if we were solving a problem right over here. We could plug in the values. We could plug in our, where's our line? This computer's possessed today. Really? Really? So we could plug in the values right here and solve. But what does all of this mean? Oh, some days, Grant, some days my brain just doesn't want to work. So with this right here, if someone told you the average GPA of UTK students was 3.8, what would you tell them? Would you tell them you believe that or you don't believe that? And also look at the confidence interval. If someone told you the average GPA of UTK students, and probably, you can include all this right here. We usually include summary statistics. So if someone told you the average GPA of UTK students was 3.8, would you believe them or not believe them? So if someone told you the average GPA of UTK students was 3.8, I swear, do you see those lines appear and disappear? Something weird going on there. Something weird going on. Shrey 100 points cracked me up too. So if someone said the true GPA of students was 3.8, what would you say? Would you say, I believe that, or no, that's a complete lie? You can't say you know it's a lie, but would you say, I got evidence against that, or that's believable? How would you respond to that? And so this, we could go through, let's go through each thing right here and tell you what each thing means in this output. Ah, I believe them. Don't worry, Meath. We're going to actually believe them. We'll go through each thing. You ready? We're going to highlight each value as we talk about it. We talked to 806 UTK students. That's the sample size. From the 800 UTK, it's a big fat lie. From the 806 UTK students, they had an average GPA of 3.80088337. We were very exact in our calculation. The standard deviation, which is a measure of variation, is 0.39. That's a measure of spread of the data. So if we drew the normal curve, we could draw the spread. Now, that's not the same normal curve down there. That's the t-test curve. But we could draw going up standard deviation. So an unusual GPA for a student would be something like 3.88. Why? Because 2 standard deviations above the mean. So you could use your mu and standard deviation right here. Technically, these are from samples, so I should use the right notation, y bar and s. Now, this is the standard error of the mean. The standard error of the mean is found by doing s over square root of n. So if you took your s right here and divide by square root of n, that would give you the standard error. The 95% confidence intervals are done by doing y bar plus or minus the t star, which is based on the level of confidence, n minus 1 degrees of freedom, s over square root of n, which is the standard error again. Just to reiterate, this quantity standard error right here is used for the confidence interval and used for the test, and that is given to you right there. So thus we get a confidence interval with a lower and an upper bound. The lower and the upper bound of the confidence interval can be used to determine things like the margin of error. So we could look at the confidence interval right here. There's the confidence interval. And from the lower to the upper, how could we get the margin of error of this interval? How could we get the margin of error of that interval? So there's the upper, there's the lower. How could we get the margin of error of that interval? So if we subtract them, really close, Grant. If we subtract them, we won't get the margin of error. Very close, though. I mean, yes, we're on the right path. I like that for 100 points. So let's go 3.835 minus 3.718. And then boom, divide by 2. There you go. So half the length of the interval is the margin of error. So subtract upper minus lower divided by 2. And you can see down here, we're showing the margin of error is this. The margin of error is this. And the center y bar is the mean of the interval. So that's the center of the interval. Now over here on the other side of this, so we've talked about all that, we have the hypothesized value here, which is mu naught. And then it even gives the y bar right there. The degrees of freedom are n minus 1 for the one sample t. The standard deviation is still just s, which we saw over there. And that talks about that. Any questions about this output so far? Hopefully all of the output makes sense right here, because now we're down to the meatier part, which is the test. So when we do the test, I thought p-value is greater than 0.5, so we do not. That means we do not reject the null hypothesis. So we got to know what the null hypothesis is. So the null hypothesis, remember, is the null states that the true mean, because we're doing a one mean test, is equal to the hypothesized value, and the hypothesized value up there, mu naught, is equal to 3.8. Now the sign of the alternative is based on what way we shade the curve, either does not equal to, greater than, or less than. So we would have to ask, maybe we're testing if it's equal to or not equal to. So that would be the first test right here. That would be the first p-value if we're testing equal to, not equal to. So right here, maybe we test the not equal to. And so now think about the wording. Ready, Meath? When the p-value is low, reject the null. When the p-value is high, just let it fly. So is the p-value high or low? When the p-value is low, reject the null. When the p-value is high, just let it fly. So is the p-value low? I think you got this part down. Is the p-value low? Is that p-value up there low? And when we're talking about low, we're saying less than alpha. Alpha is the point at which we say a p-value is low, usually defined as 0.05. So it's high, so we fail to reject. So think about now say it to me like, instead of saying I failed to go to the mall, talk to me about this null hypothesis instead of saying I failed to reject. Just talk to me more normal. Don't worry, you perfect answer right there. But pretend we don't know stats now. That's like my favorite thing to say is like, pretend we don't know stats. And we just talk about, instead of saying I failed to reject this, you could say what? This idea right here, you fail to reject it. So what does that mean? If you say I fail to reject this idea. Yep, if you turn in before midnight tonight, you got it. Yep, make sure the grader puts that on there. I did remind them via email. So shout outs to my grader right there. Huge thank you to them. They're doing a great job. Please tell me if you disagree with any of their grading. I've had one or two people email me, but believe me, I have people email me about how I grade. So one or two people have questions. I get emails about how I grade too. We can't reject it. Does that make sense? We talk very weird in statistics, or we would find it believable. Does that make sense? It seems like a possible idea because someone else could have tested, because this is why, maybe this will help make sense of why I would say it seems like a plausible idea. Could you also think it's plausible that the average GPA was 3.79? So look at this p-value right here. Is it plausible or believable that the GPA is 3.79? So not that we believe it is 3.8, but we think it's possible it could be that. Like, that is a possible truth to it. Does that p-value up there mean we think it's possible? Like, yeah, I guess it's possible that that's the GPA of the average GPA of students. So that's why we wouldn't say we believe one value is true. We would just say it seems possible. Like, we can't reject it. Does that make sense, Meath? Hopefully this makes sense right here, why saying we can't say I believe 3.8 is true. We would say 3.8 is a believable value. So 3.8 is believable. 3.79 we can't reject. That's what can't reject means, is like I can't reject it. Now watch this, Meath. You ready? I want you to tell me, do you think I can reject, and there's a hint right above here, do you think I can reject 3.833? Do you think I can reject that value? That's for 201. Yep, that's for 201 for the project, for their second project. Do you think I can reject 3.833 or not reject? And there's an easy way to know this. Do you think I can reject it or not reject it? And I'm going to put it right near what you need to be looking at. Do you think I can reject it or not reject it? Or not reject it or reject it? And I'll explain why I'm putting it right here. Do you see where 3.833 is? Where is 3.833? Where is it? When we're trying to estimate what the true mean is, it's in the interval, Meath. That's the perfect answer. It's in the interval, right? Now, it's towards the end of the interval. Meath, if you really, this is worth 1,000 points. If you can get the p-value for this within 1%, I'll give 1,000 points. I'll give you 500 points for taking a guess. Great job, Shreya, right there. Shreya knows too. Shreya, you get a guess too. If either of you get it within 1%, you get 1,000 points. If either of you get it within 1%, you get 1,000 points. Remember, you can't reject it though, but you can just barely not reject it. You have to be within 1% of the right answer on the p-value for the does not equals test. And that'll show like superior knowledge of how this works. It's towards the end of what we would not reject. It's towards the very end of what we would not reject. I want you to get it right and be like, whoa. We're going for like the deeper understanding here at the end. We've talked through the main portion of the output. Let's see if anyone has a guess. Don't worry if you're wrong. Get 500 points just taking a guess. Now I'll explain how I have a guess in my head of what I think it'll be close to. That is such a good guess, Michelle. Michelle, I'm just throwing the 1,000 points out there. That's about what I would guess. My guess, Michelle, is 0.055. Michelle, you understand it, that it's kind of close to what we would reject, but not. I wonder if Michelle or Brian's closer. Oh, it's a little bit higher than that. I'm still giving those points. Good guesses. Good guesses. It's very close to 0.05. I thought it'd be even closer. I should have gone even closer to the boundary. But good guess right there. Sure, everyone gets 1,000 points for that, but I really thought it'd be closer to about 6%. So 6%, 8%. It's towards the end of it. What I should have done is I should have tested something even further over. So if I went over here and tested the mean and tested 3.835, now you see, now I should have gone that far and we would have been like, whoa, it's right near us. Because look, this is even closer to the boundary. Does that make sense, Michelle and Meath? This is a little higher level understanding of this to be like, okay, it's towards the very edge of the confidence interval. You still can't reject it because it's in the interval. So it's like, yeah, that's believable, but I'm kind of reaching the edge of what I would say is believable. And as soon as so you're ready, one last question right here. What about if I test, and I think you'll get this, I'm going to test the value of 3.78. Let's do this. 3.780. What do you think the p-value for this is? 3.780. Last question right here, and then we're going to switch topics. Or let me know if you have any other clarifying on this. 3.780. So we're testing that value for the mean. Is that believable or not believable? What do you think the p-value is just by looking at the interval? Is that believable? Would you say, I reject that, I don't reject that? Reject that means not believable. Fail to reject that means believable or not reject. It's believable. So what would you think about that? And I hope this helps this last part of this, like, to go to the deep understanding here. I have a guess of the p-value too. We'll see what people say. We'll give it a second longer. And we're going to do some 474 project. Get to see some advanced stuff. Woo! This one, I'm going to guess a p-value of well, I don't want to say reject or not reject. This should be the easy part. Reject or not reject. I hope that's what most people should understand. Are we going to reject that value or not reject that value? Be careful. You do have to look at the decimals, and I'm giving a hint by putting it down here. Reject or not reject. Hopefully everyone knows that of this, because Meath, great practice on this. I think Meath probably knows like that. Reject or not reject. That is a hypothesized value right there. We can look at the interval. Reject or not reject that value. Reject, correct. It's outside the interval, right? And it's just barely outside the interval. It's just barely, great job, Sherry, right there. It's just barely outside the interval. So what would you guess? It's just barely outside the interval. So what would you guess? I don't want to I want to see if anyone, I want to see if someone gets closer than me. I always like that. Here you go, 5, 4. The p-value, you're trying to guess the p-value. Oh, wait, but remember, you're rejecting Meath. So anytime you reject, the p-value has to be lower than what? Using standard alpha. So this is a good review right here. That's good. Anytime you reject, the p-value has to be lower than what? If you're rejecting, the p-value has to be lower than this. If you're using standard alpha. Using just your general old alpha that we use in almost all instances, unless we say alpha's this, lower than the alpha, which is usually 0.05. Great job. So did you see the p-value I just put in the chat? I put 0.042. So great job, Mikhail. We're throwing another 500 points, people following along. So probably somewhere around there, like you just barely reject this. And so let's see. And there it is right there. You were even closer than me, earning another 500 points. And that rounds to 4%. So if you had said about 4%, you would have gotten it right just by guessing it right there. And that's the deeper understanding. That's where I hope you'll be like, okay, so we're just barely outside. So it's just going to be just barely reject. So if you're inside, it's barely not reject. If you're barely outside, it's barely reject. So understanding, that's a much, much deeper understanding of how these intervals work and how the p-values work right here. Okay, let's do some 474. Here we go. And great job, Mikhail, right there. Awesome work. Little chill music right here in the background. Phone's lighting up everywhere. Data mining. I gotta make the data mining course. Ah, great job, Meath. Okay. Let's do some 474. Get ready, Stat Tool 1. You're about to see the future. Here's some future music for you. I feel like I should have 3 cups of coffee today. All the coffee. Whew. Project. Okay. Let's do this. Here we go. Let me take a note in the chat. Final project for 474. Here we are. Now, with the final project, and we've got some help videos. Thank you so much to Olivia who posted the help videos. We're using those, so thank you so much. With the final project, you can walk through some of the kind of working with the data. Huge help videos right here. Check them out. Thank you again to Olivia who did those. Make sure I got the right. Yes. Double checking my brain. And with this right here, think about what you're doing. We are writing a report for a business. And so with this, you can use a data set of your own choosing if I approve it, or you can use any of the data sets down here. We've got census income data, we've got real estate data, we've got Australian credit approval, we've got HR analytics job of data scientist, predict who will move to a new job. So when you think about this, what you're doing is you're making statistical models and then you're interpreting those models. But I can't state this enough, that it has to be written as a good report. This is your send-off. And I should be able to, this weekend, get the rubric uploaded for it. I just want to make sure we go through all the points, because this is your send-off as a 474 student to make sure you can write a great report. Was it, I don't know if KP's still here, but KP was saying that I think their cousin or someone is writing reports like this in their job. So this is can you help people understand the data? The purpose of the project is to give students the opportunity to apply some of the data mining algorithms to what they've learned to a data set of their choosing. Once again, you can pick any data set you want. I just need to make sure it has enough. Like if you give me like a 8 observation data set, I'd be like, we can't really data mine that. It's like very small. Your written report must include an executive summary and not to exceed 3 paragraphs on a separate page. So just like a 1-page executive summary. Paragraphs are interesting because I want you to use paragraphs. Sometimes I get an executive summary that is like a bulk of just like block of text, but you want to break it apart into the ideas. I generally think of an executive summary as a kind of introduction to who the company is and what are we doing, a findings section, and then a kind of where are we going from here, like what are we doing because of this. So those 3 sections of the executive summary that I prefer are who are we and kind of what are our goals, 2, what did I find in this report, and then 3, well, what are we going to do? What is the takeaways? The project is to be completed individually. You can talk to each other, but do not send work. Be very careful of what you send to people. If there is portions of your project that are another person's project, that's going to be a huge problem. You need to upload your report and the RMD. So please don't send anyone your RMD. You can talk to people about what you're doing. You can help people understand how to use the algorithms, but you don't want to really be sending people work because that could just lead to someone copying your work. Especially you don't want to send your report or your RMD. Do meet with people, do talk on the Discord, do help each other out. Be very careful of sending, like don't send work. Like if someone wants to understand how to do something, be like, hey, can you hop on a call? Can you let me share my screen? Let me show you like how to do this. Let me talk you through it. Then have them writing the code with you. Like if they're going really quickly and they're just taking screenshots or something, be like, hey, look, I can't, I need to like help you learn the topics. I'm not here to just like do the work for you. So I know it's tough. I feel bad because I have a few students in those scenarios where they go to meet with someone and the person's just like taking screenshots of their screen. Anyways, feel bad. Had a few students reach out to me because of that. The body of the report should exceed no more than 12 pages. So once again, we have a bit of a longer report here. We talked about this yesterday in class. I mean, if for some reason you hit page 13, I'm not going to scream, but I would expect these to be somewhere between 5 to 12 pages. It really depends. There is no page limit. Um, I say that, and you can't write a one-page report. It'd be impossible. I mean, what, like a quarter-page executive summary, and the most, I don't know, maybe you turn into a flyer. Maybe someone could astound me and find a way to do it. But yeah, it's all about what you write, not how much you write. So, but you have to write something. Problems you want to answer using your analysis. So that's basically going to be in the executive summary. Make sure you're going over that. Description of the data. So this is what we've been covering a lot through the course. The description of the data is, you need to have someone understand what's going on with this data to start. Before you get into any sort of, analysis, you actually have to talk about the data, have people understand. We did a lot of data cleaning. We do some pre-processing here in a moment. But the whole idea of having people understand what your data is, what you're working with, which I think some people just jump right into the problem immediately, but we should give some understanding of what the data is and some analysis of the distributions in the data. Details on the pre-processing, what you've done, the missingness you've handled. That's something that I'm hoping to see in the current reports. List of methods you considered, but no need to describe in detail. You don't need to go into like what is support vector machine, what is neural nets. We might get to neural nets on Monday, but you don't need to go into super duper detail. I care more about kind of how you write your report and how you present these ideas than you use high level methods and bore someone with the details. What metric will be used to compare them? Does anyone right here, 474, know some metrics to compare models? What are some metrics we can use to compare models? So what metrics we'll use to compare the models? That needs to be heavily considered. So with what metrics will be used? What are some metrics to compare models? I think we still have the notes up. RMSE. Oh, look, I'm right on the page. So preferably I use RMSE, MASE, AUC. And when would you use AUC? Great job, Kirsten, right there. When would you use AUC? You could use AUC. We've kind of got it all listed right here. We basically have everything. AUC is going to be for categorical. I prefer that. And RMSE is going to be for quantitative. Now, you don't have to use RMSE. Preferably, and Rob Hindman knows, for logistic regression, then you'd be using AUC, because AUC is going to be for categorical. So this is classification right here, and this is quantitative. Stat 201, we're still talking about categorical and quantitative, even in 474. Great job, MK New right there. You can use RMSE for quantitative, so you have to know what kind of Y you have. Also, a huge thing right here, too, is when it comes to the Y variable of interest, that's going to be a huge thing in how you set up your what. How you set up your what. When we talk about the Y variable, I've got this so nice and organized right here. When we set up our Y variable, the Y variable is going to be a huge part of how we set up our what. The Y variable of interest, and these were notes we took yesterday, the Y variable of interest is going to be a huge part of how we set up our fit control. Because if the Y variable is quantitative, we're usually going to fit, and you could fit on another metric. I prefer RMSE if someone really loves MAE or MA. I don't think we can get MASE right here. So for those in 475, I don't think it fits towards MASE. In addition to my Shiny app question, I'll have a candidate question. Yeah, okay, cool. Yeah, oh, that's cool. Yeah, no, definitely. And then, sorry, no, I haven't responded to the Shiny yet, but no, I will. I've got it running, and then I saw, and we'll look over where you're having the issue with the forecast. Thing us so much. But yeah, if you want to use the data set right there, that'd be awesome. Yeah, I want people to use I love it when people use a data set that they are interested in. And then just make sure you know how to set up which metric you're evaluating it on. Results of your selected method, description of the results, and which methods perform the best. Aha. Now, this is where we get into those cables that we were making. Cables are like really nice tables. I highly suggest, so for those watching it right now, I highly suggest using the cable output that we have. I'm trying to think, check out yesterday's class or ask me about cables, but shout outs to Sierra right there. If you are doing this and showing your models and which models work best, probably maybe even jumping in. If you don't know how to make a cable inside of R, don't worry. I'd probably just put it into Excel and then take a picture of it in Excel. Like take your output and put it into Excel. Probably the easiest way for a lot of people. To do that right there is just like, let me take these numbers, let me put it in an Excel table, screenshot the Excel table, drop that into my Word document. Think about making things look nice. You are going to be graded on how this looks. I know, just excellent work right there. We were trying to get the, what package were we working with? It was a longer name. It just wasn't doing it. And then someone else had a better package. There's a lot of table packages in R. Interpretation of results. Focus on the highlights of your analysis stated. Yes. Report on variable importance. That's the var_imp function right there. Just tells you the importance. We saw it on Wednesday's class. We saw some variable importance. It's kind of important, but that's a little more descriptive modeling. So I'm not like, of all the things I wrote right here, not the biggest on that. It's appendix containing any useful resources. This includes the 12. This is included in your limit right there. So appendix, anything you've used, any sort of ideas, especially if you're talking about, maybe the methods from Carrot or things like that. But this should look like a super professional report. Like format table, yes, Trey remembers right there. Cable is better. So yeah, what are the questions about the project right now? So basically, this is a little bit open-ended. It's more formatted towards you to kind of pick your own path and analyze data on one of the metrics. So I'd probably be picking RMSE or AUC, which means you need a Y variable of interest. You want to know if your Y variable is quantitative or categorical, and thus that'll set you down the path of RMSE for quantitative, AUC for categorical, and we'll be seeing some more models today as we go through, because we're going to get into tree-based models. So there are a lot more models to pick from, but at this point, you have under your belt the ability to do GLM and GLM net. For those in 474, do you feel comfortable right now doing a GLM or a GLM net? And if you're wondering, if you want to start doing more models, if you go here into the data mine, here's the link for how to use cable. Nice job, Sierra, 1,000 points. Sierra, thank you so much for all your help and all your great contributions right there. And I mean that to somebody, I can name a lot more people in the chat who are giving, like Shreya, I got to shout out Shreya too. And Noah, I'm just going to shout out everyone. Finish. There we go. So thank you so much for your contributions right there. Dropping some links in the chat. That's what we like to see. So with this right here, you can jump down to GLM. You can jump down to GLM net. GLM net, you need the GLM net grid. And we've gone over the theory yesterday on how to use the GLM net grid and what it means. And Noah, great questions yesterday about the values on the GLM net grid and what we're doing here with alpha and lambda and what values of alpha and lambda should we pick. And that's the way a lot of people do it with the lambda raised to. It just does decimals right there. There are no exact values, and if you bring your buy down, you get a much cooler rainbow graphic where you see but it takes a lot longer to run. Power boost acquired. Now, if you want to go crazy, you go to XG boost. XG boost. We got XG boost on here? You go to boosted models, boosted trees. There we go. What do you notice about the boosted trees? There's a lot more what's. Can anyone finish my sentence? I'll give you a hint in a second. But on the boosted trees, there's a lot more what's. On the boosted trees, there's a lot more what's. On the boosted trees, there's a lot more what's right there. There's 4 tuning parameters. Kirsten, you're right. There's more tuning parameters. Now, here's a really good question. How many models would this make right here? It actually doesn't make that too many crazy. There's more tuning parameters on boosted trees. There's the number of trees we're using. There's the interaction depth of how many times the trees are being built down. There's the shrinkage, which is the learning rate, and the number of min observations in a node. And the number of min observations in a node for how small a tree can have material in it. A little bit on this stuff today. So how many models would this make? You should know how to figure this out. It's the same question we did yesterday with how many models. Let me see if I can figure it out. It's not that crazy. Okay, I think I know the answer. Let's see if anyone else confirms the answer. How many models would this make? And I'll show you how to find the answer. I'll give you a little hint while we do this. And we're going to go to 474. So how many models would this make? 36, yep. Because... So what do you do with this right here? What do you do with this info that I'm putting on the screen? This is how many values are in here. There's 2 ways we're doing this. There's 3 ways we're doing this. There's 2 ways we're doing this. 3. So 2 times 2 is 4. 3 times 3 is 6. And wait, did we make a mistake? 3 times 3 is 9. Oh my gosh. 4 times 9 is 36. There we go. Brian can't math today, but it is 36 different models. And you could just run it and take a look. And you could see right here, there are 36 different models doing all the combinations right there. So just understanding questions like that are pretty important, because the issue becomes if we were to do something like this right here, which is a bit ridiculous. Now what happens, the grid gets really crazy huge. We can't even see it. It's got 60,000 different models in it. So this is where you would crash your computer, Kirsten. Probably, I don't know, maybe you got a really awesome computer, and we probably wouldn't want to do interaction depth 100. It's pretty crazy. Interaction depth is how far you let the tree grow before you stop growing it. When you're making trees right here, because this is boosted trees where a tree learns from a tree. This is partition modeling from Stat 201 where we do decision trees. But now we grow a tree, and then we learn from the tree, and we kind of build another tree next, and we learn from that tree. We build another tree, and we learn from that tree. This is the minimum number of observations that can be in a bottom leaf of the tree. Just so you can know what I'm talking about right here, and we can link this, and we're going to change topics. We're literally talking about an algorithm. I think you can do this in Jump even. We're talking about an algorithm right here where you go in and check down here. Boosted tree. Jump has it. We're talking about an algorithm where you're trying to predict someone's gender, and you're using these variables. And so what it does is it grows a tree. I hate that the points are colored. It grows a tree, and we left an identifier in here, and it grows it to a certain amount. This is the interaction depth right here. This is an interaction depth of 3. And then it learns from this tree, and it takes that information and builds another tree with the information it learns. And so it starts over again now, and it builds another tree, and it's using the information each time to kind of grow its understanding. So we could actually do this inside of Jump. We don't want major. Go to relaunch analysis. Let's remove major. I rarely do it inside of Jump, but I want to see how Jump looks when it does it. So here's major. And I think there was one other one. I can't remember what it is, but let's go down here to boosted trees. And it brings up a secondary thing when you do it here. It brings up like yeah, here it is. Number of layers, splits per tree. That's the interaction. See, look, you can't even do tuning. You can't go across tuning parameters. You have to put in the parameters you want for the one way of doing it, which is a bummer. Splits per tree, interaction depth right there, number of layers, use that terminology, learning rate, that's your shrinkage right there. Overfit penalty, that's regularization right there. So they've got different boosting parameters right here than we do. But they don't let you do a use tuning design table. There we go. There's the tuning parameter table, which I've never used in Jump, but there's their boosted trees. And there it is right there. There it is. We got R squared. There's our R squared. Pretty cool. A little bit, you don't get to see what's going on, but neat stuff. Really don't use the Jump platform much for that, but I guess you can use a tuning grid inside of Jump. I haven't done that. Anyways, that's what we're doing with code, and we're writing our own tuning grid over here and choosing the parameters. This is gradient boosted trees, but there's also extreme gradient boosting. Last thing I want to show you is extreme gradient boosting. Extreme gradient boosting is where things get crazy. Where is it? Oh, methods and sidetrain. Extreme gradient boosting. What do you notice about this? What's the first thing you notice about this with extreme gradient boosting? What do you notice versus what we've been doing? What do you notice right here about extreme gradient boosting? Which this, I wish I was a pro at this, because this is where the real power is. Lots of tuning parameters. Lots of tuning parameters. So many things to do. Shrinkage is probability of skipping dropout. Even I was able to join. Have you gone over? Yeah, at the start. Check it out, Nolan. Definitely. Let me know if you have questions. So, Kirsten, you're right. There's tons of tuning parameters right here. And you see there's also multiple ways to do extreme gradient boosting. So there's different extreme learning machine. I think statisticians just like to put extreme in the name of what they come up with. So there are there's using XGBoost. XGBoost is the top package for it, and then Plier right there. So yeah, package XGBoost. Yeah, so they're leveraging XGBoost to do it. So make sure you have XGBoost installed. If you don't, you need to get I don't know if I have XGBoost right now. I do. There we go. Extreme gradient boosting. Yeah, that's that right there, Kirsten. Extreme gradient boosting is probably some of the most powerful models we have due to the kind of way in which it can learn from the data and the high level of things we can manipulate to go through different models. So if you're really looking to make something super great, extreme gradient boosting is one of the top ways to go. Super duper complex, and that's the biggest problem with it, is that it's so complex that, would you be able to communicate how you made the model to someone who doesn't really understand statistics? Maybe not. But hey, if you're just looking to make predictions, you'll make some great predictions. With that, let's do some 475. Thank you, Sierra, for your questions. Let's head over. Awesome. Thanks so much, Kirsten. Hopefully some extreme gradient boosting. We'll be getting to that. That's kind of very last things we talk about with neural nets, extreme gradient boosting, support vector machine, some of the big ideas. And all you have to really know is you're working with tuning parameters, trying to figure out the knobs and dials to turn to get it working. Oh no, Mubot asked out statistician and she failed to reject him. Oh my gosh, Mubot, really? Really, Mubot? So perfect. I'll look into it. I think I found a data camp. Whoa, Kirsten, I need to look into that. Like, I do some extreme gradient boosting, but it's like one of the top level things. Like, it's like, yeah, like I can run the algorithm. I mean, I can just put in some tuning parameters. But hey, Caitlin, good to see you here. Kirsten, I should do the data camp course on it too. And actually, we're reaching out to data camp. I have a meeting with them. I want to get some more info about integrating it into classrooms. My dream is that we could actually assign data camp courses and just have it integrate into our classes to where it's like, okay, you need to do this, and it just pulls the grade from data camp. I don't know if they have the right LMS integration, but hopefully we see that. So I'm really excited about those possibilities. Okay. Let's do some 475. 475. Okay. I know, it's so cool. We do the other models. How do you graph it? Oh, so you can still just plot the. Oh my gosh, right, Sierra? Because there's too many parameters, right? So you might not be able to graph it. If you have that many tuning parameters, what it'll sometimes do is it'll do like a grid, because you can only put on a X and Y grid two variables, right? But then it'll do a grid of the other variables, and I think it makes subplots of contained within. You might not be able to graph really easily all your tuning parameters, but you could instead just look at the list and see where the best RMSE is. But because that's what you're doing, you're picking the best tune. But with that many tuning parameters, like 6, 7, 8 tuning parameters, it's gonna be very hard to make a graph that accurately represents like where are you at. So that's why it's so complex. Is you're doing got a lot of options, a lot of possibilities. So good questions. Let's hop over to the main screen. I love hearing those questions about it because there's so many big ideas that we're getting into right now. Okay, it is time for some AIC, which we'll be going over today. So what is AIC? Does anyone know the gentleman AIC is named after? What is AIC? AIC stands for Ake-Ike's information criteria. Ake-Ike. And here it is right here, expressed. I like it. Dr. Humphreys Bosdigan talks about Y2K. I don't know if that's a joke he made up. Ake-Ike, yep. And so the gentleman Ake-Ike is a famous Japanese statistician. One of the people in my department, Humphreys Bosdigan, was a pupil of Dr. Ake-Ike. And Hirotoga Akeike, where is he? Should be on here somewhere. He actually had a real strong relationship with UT because of that, in part. There he is, right there, just top tier statistician, really great guy. Probably butchered the spelling. No, close-ish. It's down there, Akeike. But he like he was given Japan's highest award. So where's it? Awards and honors. He was given right there the Kyoto. In 2006, Akeike was awarded the Kyoto Prize. The official citation states the prize was for his major contributions to statistics and science modeling with the development of AIC, Akeike's information criteria. One of the top fellows. Even Google honored him with a Google Doodle. I do remember seeing that and being like, wait, what? So, and shares a birthday with someone I know. Cool. So really cool stuff right here. But all this stuff right here, Akeike, just a huge contributor to what we do in statistics. So then you might be wondering, well, what did he come up with? He changed the way we view modeling. He started what is really called, or he really didn't start it. It was Lawback and Kobler, this thing, two Russian statisticians who have this whole information. He kind of expanded upon it and became the one who took it to the next level. There's the idea of information school of knowledge, like the information school of statistics. And what we're looking at is how close our model is to the truth. And it's super complex. Like the stuff he did right here on figuring this all out and showing that it works. There's BIC, which is the Bayesian information criteria. There's also FIC, the Fisher information criteria. He basically went through, there you go. There's another information criteria. I don't even know of this one. But there's another one. It might be more recent. Huh. I don't know. One site it seems to have been, yeah. AIC is where it really took off. Oh, it's the focus? I thought it was Fisher. It's the focus information criteria. Yeah. So the big thing to know is when we're talking about information criterias, I have to see this. There is a Fisher information criteria. Fisher information. Oh, it's Fisher information matrix. Bosdogan. That is literally, Bosdogan is University of Tennessee. There he is. There's Dr. Humphreys Bosdogan. I'd have to read over the paper, but he's using ICOMP right there. That is his information criteria. Talked about that, but there's Dr. Humphreys Bosdogan, Department of Statistics, University of Tennessee, Knoxville. So one of the pupils of Dr. Akeike. But huge shout outs. 79 citations. That's pretty crazy for a paper as far as I know. But yeah, pretty big stuff right there. And Dr. Akeike and was the professor or famous statistician who Dr. Humphreys Bosdogan. And it's really amazing to hear Dr. Bosdogan talk about this. He actually went to a conference where Dr. Akeike was at. I think both of them were presenting, and he went to a presentation with Dr. Akeike, kind of talked to him afterwards, and then Dr. Akeike showed up to his presentation and invited him to come to Japan to study under him, I think in a postdoc. So really amazing story, and that was back in the 70s, I believe, when Dr. Akeike took on Dr. Humphreys Bosdogan as a pupil. And so huge shout outs to both two amazing professors who have done amazing work in the realm of statistics. Anyways, enough about people in my department and those who have led the way in these big ideas. Why does it all matter? So when it comes to AIC, what we have to know is we're trying once again to take the least bit of information from our variables. So we call this idea, starts with an R. Does anyone know the idea of when we're taking like the least amount of information possible? So we're limiting the scope of the information we're taking. So we call this what? What do we call this? I'm going to do a very basic way to describe AIC. So when we're limiting the information we're taking, we think of this as a what? And funny enough, this goes back. Where is it? We had it open a moment ago. It goes back to what? When we're limiting the information we're taking, what do we call that? Ozium would love that. Regularization. 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 So we're limiting kind of the amount of info we're taking. And we talked about this yesterday with the elastic net regression. So yesterday we went over elastic net regression and we did a big review. We started Wednesday and then we kind of went into a big detail at the start of class in 474 with elastic net regression and kind of limiting the amount of information we're taking. So how does this equate to Ake-Ake's information criteria? Well, with Ake-Ake's information criteria, you have right here, basically, you're trying to optimize Ake-Ake's information criteria. The lower it is, the better it is. Difference of more than 2 is substantial, is something. It's something. What do I mean by that? It's a big, like not a big difference. I think of 10 of a bigger difference. Difference of more than 10 is large. Let's say difference of less than 2. So there's no interpretation of it. There's no, we have this much information, we've lost this much information. We just compare models with it. So you could use this to what your models, Sierra and everybody, you could use AIC to what your models. And that's why they're over there in a box. It's the focus information criteria. I thought it was Fisher. I guess Fisher came before, so it wouldn't be him because he wasn't around at that time. So you could use all these right here to evaluate your models. You can see how your model is doing with the AIC of your model. Does that make sense? The AIC could just be used to say, how's my model doing? Is it a good model? Is it a bad model? And when we use AIC, the lower it is, the better it is. The lower the AIC, the better the AIC is. And with this, it's kind of easy to understand the equation. The equation for AIC could be summed up the following way. It's simply going to be the log of the error, and then plus penalty for variables. What is the smallest error we could have? What is the smallest error our models could have? What is the smallest error a model could have? Does anyone know when it comes to error, like sums of squared error? What is the smallest error a model could have? So you think you build a perfect model. What is the smallest error a model could have? 0, sure, you're right. So then what is the lowest AIC information criteria? The lowest AIC information criteria could be what? Kirsten, I think you switched accounts there. What is the lowest AIC information criteria? If the smallest error would be 0, just take right here. Not quite 0. Close, Noah. Well, no, I think you're saying to the previous question. Good work right there. So if the smallest error is 0, and maybe we got a big penalty over here, kind of negative, but so what is log of 0? Well, that's right. That's right. But what is log of 0? Do you know what it is? Lower is better. Why is this model good? Just explain to me with this right here. Why is this model so good? Negative infinity, yep. And so why is this model so good? The model has no error. This is the regularization part of it where you're penalizing yourself for variables, but this is a perfect model, so the penalty can't overcome the perfect model, or the penalty is not damaging us because it's a perfect model. I still would worry about overfitting with this. A lot of algorithms are smart enough these days to not do such a thing right here because it's going to stop because the AIC is not lowering. It's not going to just jam a bunch of variables in the model to make it work perfectly. But you can run into this scenario where you have an AIC of negative infinity. That doesn't mean you have a perfect model. So the lower, the better, and it just goes more negative. I've had people see a negative AIC and be like, that's bad. And I'll be like, no, that's good. The smaller it is, the better. It just means probably your error and had to be somewhere less than 1 because if you get an error of 1, it's going to be 0. So especially for small values, like if you're working in like decimal values, you could get a very low AIC. There's no interpretation of AIC. It's just used to compare models. Just used to compare models. So you don't interpret it. You just use it to compare models. So let's make some AICs here. Okay, we need to make some models. So we should be able to go to library FPP3, and let's go to some arrivals. There we go. Let's filter by Japan in honor of Dr. Akaike. So origin. There we go. We've got the Japanese arrivals. And then let's go in here and make two models. Model and naive equals. Cool. And it's seasonal, right? Is it seasonal? I think it is. I shouldn't name things the same names. There we go. Got two models. Practice your model. Random walk with drift equals RW tilde drift. Is it not? There you go. It did it. I don't know why they didn't autocomplete. Well, it did now. Okay, now we should, fingers crossed. Oh, we need to, I think we need to do a forecast first. There we go. Forecast. Oh, wait. Glance. There's no glance method. What? Double check over here. I thought it'd fit. Let's see. Let's get the AIC. Let's get the... Is it Maya? Did you mean Tibble? There's no method of glance. Is the glance picking the wrong glance? Let me look at the glance I'm using. That's Fable Tools. And okay. So it is giving the values right here. I like silence. Put on the music right. I'll figure out the issue. Sometimes the code doesn't do what you want it to do, so you get the code to do what you want it to do. Okay. Okay, let's take a look. You do not need forecast with glance. Oh, you just used the model fit. Oh my gosh. Is that it? If you pipe the wrong thing through. And then we're getting the sigma. Now, it should have the other values. Let me look at the methods. Sierra, great work right here. 500 points, Sierra. We're going to end off with this. We should be able to get... Are you getting it now, Sierra? Just going to pull some AICs. Glance of the fit. Yes, we take that. We're not getting our AICs. We're just getting the sigma right there. Why are we not getting our AICs? Oh, well, time series. Whew. Oh, you're wondering how to connect into the time series cross validation. Whew. Oh, we gotta. Well, one, that's gonna take a while to run. Whew. Sierra, message me on Discord and we'll get that running. Why am I not getting my AICs? Is it mad because I'm using multiple models? Why am I not getting my AICs? Let me go grab... Let me do it the exact way, and then we gotta end off here in a moment. Why? Oh, why? Let me grab the models they make right here. my song. Should be able to do it. Time series linear model. We should be able to get it out of other models. I might need to take a look, Sierra. I stored them all and then did a glance on the store ones and it worked. Yeah, that's what I thought. There's the model stored. There's an ETS right there. And then we should be able to go to fit. There's the glance. Okay, so now, let's see here, because you're wondering on the time series cross-validation. Okay, how big is this? Okay, this isn't a huge data set. Let's try to do it. Ready? Speed run time. Let's do this. Let's go to this. Let's go to stretch Tisbel. And let's go to stretch. There's the stretch Tisbel. Nothing too crazy. Let's go here and take our models on this. Okay, there's our model. Let's store it into fit 2. Okay, so now we're making the model on this. Let's see if it just runs right here. You might not be able to get the AI. I don't know, just the way the stretch Tisbel is that it's making multiple models. The glance might not work on it. You could then just use RMSEs. So as you can see, it's taking a while to fit the model right here for the, should have maybe brought down the stretch on it. Let's see. 2 seconds, let me get everything going. We'll let this run in the background while I get the last few things going up right here. We want to get it working. Bunch of warnings. That's all right. Oh, because it's predicting outside, I think. Okay, so we should have fit. Okay, we got the fit. Good. Null model, that's fine. What we might have to do is we might have to remove those. Oh, there it is. Good. So here's the issue, Sierra. You see, it didn't do the first 3. No, to become not changed. So what it's doing, remember, probably what I would do, Sierra, is I would take right here. I'd call this table. And then inside my table, I take my AICs or AICCs, probably AICCs, and then we want to subtract off the 4th one on it. There's all the AICs. Ooh, look at those AICCs. Or those AICs. The model, something. The model is showing that it's further from the truth towards the end. We don't have consistent AICs in the predicted power of the model. That's what I'm learning from this. Does that make sense, Sierra? You get a lower AIC here to start at the start of it, and then towards the end, when this is doing the stretch Tisbel, which we talked about yesterday again, we're getting much higher AICs, so the model is not internally consistent. That's an issue to me right there. So this is what I would look at and what I would communicate to someone. I don't know how to... I could think, you know what I could do with this? We might be able to just auto-plot this. I'd love it if this just auto-plots. Please auto-plot. No, it doesn't like it. We could plot it. There we go. Then we could talk about making this look nicer. But your AIC is steadily and linearly increasing throughout the model, showing that the model is getting further from the truth. And that is a fear of mine, that you'd want the AIC to remain relatively constant as you do a stretch Tisbel. Does this make sense, Sierra, right here? This was a really good question, and I think this is the answer to the question that I have some fears with this model right here, that the model as we go further into our stretch Tisbel is getting worse. And that's what the AIC is communicating to me right here. And I would put this in a graph and present it to someone in a much nicer format, give it a nice GG scatter, and talk about the model here does not look to be reliable throughout. Thus, if we look at the AIC, you see, I'm a little afraid to even estimate it by this. Oops, didn't do a thing around it. I don't even think we'd get an AIC of about 100-ish. The original AIC shows an AIC of better 200, and where were we at? We were up towards the 200 at the end. So it's not a consistent AIC throughout. Yeah, pretty interesting right there. And that's how you could do it with the stretch Tisbel. It's interesting to me that it did so well at the start, and then by the end it was really bad. But yeah, so basically he's doing... Oh, it's got the same value at the end. Looks to be just going further from the truth. But it might also be taking more information from it. Yeah, I need to think about what this is meaning more and like interpreting it to someone, but because it might just be that the ETS is taking more information at this point, and then early ETS is using minimum information. But truthfully, the model, because it might always have this. But good question, Sierra, right there. Really makes me consider, but I don't think you're going to get a good AIC estimate from this. So I would probably keep back to your RMSEs, which we should be able to get right here doing an accuracy on this. I'd probably, using your stretch Tisbel, go over here and do accuracy on it. And we should be able to get... Dun, dun, dun. There you go. And it's making it across all the models. So there's your RMSEs right there across all the models. So with that, we'll be back doing class here for 475. Coming up here soon. Bye for now, everyone. Bye!